Okay, so for homework, I asked you to identify the translations, the everything that was happening with our trig functions. All right, so I gave you one cosine example, one sine example. Now, all of these things, both of these functions have the same properties, right? So they're similar in that aspect. So we can change it up that way. So for the first one, we have 5 minus 3 times the cosine of pi x minus 2. All right, so first for the amplitude, remember the amplitude is always positive no matter what's in front of it. So your amplitude is 3. Right? It would have made sense to have an amplitude of -3. That would be saying like, if you're in geometry, you measure the side of a triangle and it's -5 units, right? It just doesn't make sense. It doesn't. The concept of amplitude doesn't involve negative numbers. Next was period. Here, our b is pi, right? That's the number that's next to our variable x. So when we set up 2 pi over pi, that gives us a period of 2. All right, so be careful there. Our horizontal shift left and right, remember that goes opposite of what we see. So because we have -2 on the inside, that means we're going to shift right 2 units. And then on the outside, that's our vertical shift, and that follows whatever sign that we have. Now in front of this 5 is an invisible positive sign. So that would be a vertical shift 5 units up. All right, so for your first problem, you had these 4 translations. Amplitude is 3, period is 2, horizontal shift is 2, and the vertical shift is 5. For our second one, similar situation with sine. All right, here the amplitude is already positive, so your amplitude is 4/3, right? Positive 4/3. The period. Here, my b is 1/4. Okay, I can separate this x over 4 to 1 over 4 times x. So when we divide 2 pi by 1/4, that gets us a period of 8 pi. Remember, right, we talked about it yesterday. When this is a fraction, when this is less than 1, that stretches our graph out, right? It makes the period longer. So a period of 1/4, it would be really squished together and you'd have a lot of peaks and valleys that happen quickly, right? So our period is 8 pi. Our horizontal shift, we have a +1, so it goes in the opposite direction, 1 unit left. And then we have -2, so that would be a vertical shift of 2 units down. All right. Now, again, you could have graphed these to see what's happening as well, right, to compare the two, the original with all the translations. Right? Any questions about the homework? All right. So today we're just going to take some time and we're going to look at the graphs of our other trig functions, right? Sine and cosine are our most basic trig functions. Everything else, the other 4 are built off of sine and cosine. Not built off of, but they involve sine and cosine, right? So we can use the properties of our sine and cosine graph to help us. Oops, no, let me get rid of this. I don't need that anymore. There we go. We just need, all right, let's take a look. We'll start with a tangent. All right, so remember, tangent is the relationship or the ratio of sine to cosine. Right, so there's a few things here that help us shape our graph of tangent. Now remember, tangent is one of our trig functions that can be greater than 1. Sine and cosine, unless we mess with the amplitude, the range is from -1 to +1. But as we've seen when we looked at the triangles themselves and we did the trigonometry with triangles, I can get a value greater than 1 with tangent because of this relationship here, the sine over cosine. One of our restrictions is that we have cosine in the denominator, right? So we can't have cosine equal to 0. So going back, right, we know that there's a lot of instances where cosine is equal to 0, right? It crosses the x-axis a number of times. So here at pi over 2, or 90 degrees, cosine is 0. So what that means is when cosine equals 0 on the graph of the tangent, going back to, I'm going to draw this x-axis pretty long. Okay, going back to our rational functions, anytime we have a 0 in the denominator, that gets us a asymptote, right? So at pi over 2, at negative pi over 2, at 3 pi over 2, at negative 3 pi over 2, and we can keep going in both directions forever, right? We're going to have vertical asymptotes. Right? And again, at all of these, we get these vertical asymptotes because cosine is equal to 0 there. Right? Cosine of pi over 2 is equal to 0. Cosine of negative pi over 2 is equal to 0. So now what happens is we kind of get a repeating function. Right? Well, the tangent of 0, we get 0 over 1, so that's okay. So the tangent of 0 is 0. Now, the behavior of this looks like a cube function. Right? So we use these asymptotes to kind of guide our trig function, our tangent function, right? So it starts off increasing, it kind of flattens out as it goes through 0, not completely flattened, but the slope decreases, and then it increases again as we go up. Now, all of these other little areas are pretty much just a copy and paste of this. All right, so here, in between pi over 2 and 3 pi over 2, hold on. Oh. All right, so here at pi, here at negative pi, where sine is equal to 0, we have x-intercepts. All right, and then over here we would have 2 pi, and at 3 pi, 4 pi, 5 pi, they would all be zeros. Right, and our graphs, each part follows the same pattern. So our tangent function is a repeating, increasing function. Right, so it starts, it comes up, asymptote, and we have the same pattern, asymptote, pattern, asymptote, pattern, asymptote, and it goes like that both ways in all directions. So here we do still have a period, right? A period just means any time that our function repeats itself. But now our period is a little bit shorter. It goes from pi over 2 to 3 pi over 2. So my period isn't 2 pi anymore. My period for tangent is just pi, because we throw that cosine in there as well, right? So where they overlap every time is the period. Okay, our domain is restricted, right? So we say x can't equal, now this is a different way of looking at it. So we say that the domain x can't equal pi over 2 plus pi times n, where n is some whole number. Okay, or in more mathematical terms, we call it a natural number. Right? So pi over 2 plus pi, right? If n was 1, would give me here. Pi over 2 plus 2 pi would give me 5 pi over 2, which is over there. And then if we go in the negative direction, then we have that. My range is all real numbers, right? Even though I'm restricted for my x values, my range in between these two asymptotes, it goes all the way down from negative infinity all the way up to positive infinity. And then it repeats that. So that's something that's pretty interesting about that. Right? And our x-intercepts we can find by doing n times pi. Right? So our x-intercepts are at all of our whole pi's. So pi, 2 pi, 3 pi, 4 pi, 0, negative pi, negative 2 pi, negative 3 pi, so on and so forth. All right, so there is our tangent function. Our cotangent function. Oh, that's not how you spell cotangent. Well, we know that cotangent is the inverse of tangent. Right? So it behaves somewhat similar, but because sine is in the denominator now, our asymptotes are where sine is equal to 0. So here at pi, here at negative pi, here at 0, it's kind of hard to see when I try to make a dotted line there. Okay, so we have that sine can't equal 0. Get this mouse out of the way. So the other part is now that we have these flipped, these are reflected. So instead of increasing in every interval, we decrease. So again, this also has a period of pi, right? From 0 to pi is pi, and then the next one would be 2 pi, right? That's where my next asymptote would be, so on and so forth, and in the negative direction. So we say our domain, okay, can't be any natural number times pi. All right, so 5 pi, 10 pi, negative 20 pi are all off the table. We can't plug those in because that would give us a 0 in the denominator. Again, our range is all real numbers from negative infinity to positive infinity. So now our asymptotes and our x-intercepts swap. So my x-intercepts are going to be at pi over 2 plus n pi, comma 0. Right, I'll put some. Okay. Right, these two are directly related because my domain can't be n pi, my asymptotes are n pi. All right. Now, the other two are really interesting. So we'll look at cosecant first. So cosecant is the inverse of sine. So we have a few things happening here. So again, our sine function, we have zeros for sine. So for cosecant, we're going to have more asymptotes, right? Right, so like our cotangent function, we're going to have asymptotes at our whole numbers, right? Or not our whole pi's, right? So at pi, at 2 pi, at 0, at negative pi, right? And we continue like that. So what I'm going to do here is I'm going to draw, I have another color. I'm going to draw, just for reference, our sine function. It's not going to be perfect, but you get the idea. Okay, so the blue dotted line is our sine function. So we can see where the sine function crosses the x-axis, that's where our asymptotes are, because we have that. Now, the way the graph behaves in between is an alternating parabola. So here, our graphs intersect. So again, this blue one is our sine function. So our cosecant function is almost like a mirror image, but it goes up forever. So here we have a parabola that fits in between these asymptotes, and it points up because this part is positive. Here, we're going to have kind of a parabola that goes down, right? Same thing over here. Up here, we're going to have that upwards parabola. So our cosecant function is going to have these alternating parabolas that correspond with the maximums of our sine function. So here, the minimum of the cosecant is going to be the maximum, the relative maximum of our sine. All right, so let's look at an, let me type this out so we can look at the actual graph and not my crappy drawing. All right, so there we have our cosecant. Let's compare it to our sine. All right, so there we can see. So at x equals pi, no, come on, x equals pi, x equals negative pi. All right, we can see our asymptotes there, x equals 0. And then these parabolas, again, they're not exactly parabolas because they don't behave like them, but they look like them. They fit in between those asymptotes, right? And then I can even keep going, right? X equals 2 pi, x equals negative 2 pi. Right? So because they're inverse, they behave oppositely. Opposite. Yeah, I guess. Right? So when we're talking about the domain and range, we get some interesting things. Well, first, my period is back to 2 pi, right? Because it takes from negative pi to 0. I don't repeat anything until I get back to positive pi, right? So from going from negative pi to positive pi, that's a period of 2 pi, right? Negative pi plus pi. So my period is back to 2 pi because it takes me that long to repeat what the graph looks like. Okay, my domain, I have the same domain as my cotangent function. My range is interesting now. It's not just all real numbers. If you notice, we don't go below or above the sine function. So for the range, we're going to write it like this. So we have from negative infinity to negative 1. All right, so remember, I use the parentheses with negative infinity because we can't equal negative infinity. I use the bracket with negative 1 because it can equal negative 1. We're not going to have any answers in between negative 1 and 1. Right? So if I took out, this blue line, this blue dotted line, my graph will never go above negative 1, but it won't ever go below positive 1. Right? It's allowed to be outside of that range, but nothing in between, nothing where the sine function is. All right? And then another interesting feature of this is we don't have any x-intercepts, right? Because the way our range behaves, our function can never equal 0. I can never have 0 here, right? Because I have that 1 in the numerator. If I divide by 0, it gives me an asymptote. All right? Well, we're running out of time, so just real quick, get rid of all these. Our secant function is similar to the cosecant, but the secant function behaves inversely to the cosine, right? So now you can see here we have a y-intercept. Before we didn't have a y-intercept, right? But everything else is the same. We meet here at the maximum and minimums, but now those are positive, or not, I'm sorry, whole number pi's, right? Pi, 2 pi, 3 pi. And our asymptotes would be at our half pi's, right? Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, positive pi over 2. All right, so the secant and the cosine have the same relationship, or a similar relationship, as our cosecant and our sine. Right, so you can kind of see, if I get rid of these, right? I've mentioned this before, but sine and cosine are very similar functions. It's just a phase shift of 90 degrees. Right, so the difference between this point here and this point here is 90 degrees. I moved over pi over 2. Right, so I did a translation. If I take sine and I do sine of x minus pi over 2, that equals minus. Oh, I'm sorry, maybe plus. Yeah, okay, there we go. Plus pi over 2. Right? Well, that's the same thing as cosine. So similarly, our cosecant and secant are shifted just like our sine and cosine are. All right, guys, thanks for sticking with me to the end there. Any questions?
Not gonna lie, it's kind of like a bit confusing, but it's okay.
Yeah, I agree with Carmen.
What's confused? The actual graphs or how they behave, or?